Hello, my name is Johnny Birch, and I am an engineer at Intel. A segment of the Function as a Service, or FaaS, ecosystem has adopted WebAssembly as a core compute technology, and Intel hardware, specifically Intel MPK, can make this up to 15 times more memory efficient by increasing the number of available WebAssembly instances. As a quick primer, WebAssembly, also known as WASM, is a target binary for high-level languages such as C, C++, Rust, Go, and many others. A WASM binary is a bytecode-like format that is executed by a WASM runtime on the host environment. Execution environments include PWAs and browsers, as well as standalone or headless cloud or edge environments. Here, our focus is cloud and edge, and specifically, WASM deployed within a function-as-a-service infrastructure. Function-as-a-service providers typically run third-party functions in a cloud environment, such as AWS Lambda, responding to HTTP requests from users by executing the untrusted functions in a sandbox of some kind. Some function-as-a-service providers have adopted WebAssembly as the target of choice for these functions, relying on WebAssembly's sandbox protections, near-native performance, and fast startup times. In these environments, a user sends an HTTP request to the function-as-a-service provider. The function-as-a-service provider instantiates an untrusted third-party WebAssembly function, and the function executes, returning an HTTP response to the user. WebAssembly runtimes, such as WASMtime, are designed to instantiate and execute quickly. They do so by imposing limits on the WebAssembly's memory. For example, by fitting the WebAssembly function into predefined slots in an instance pool. These slots are kept warm to speed up function instantiation. The function-as-a-service provider's value here is that the requests are serviced faster and closer to the user than they would be in the third-party customer's infrastructure. But what happens when the WebAssembly function has a dependency on some other service? Imagine, for example, that a function looks at a user authentication token to retrieve some data from an authorization server and appends a header to the request. While the function is waiting for the external server's response, the function is idle. It may not consume CPU cycles, but it still occupies a slot in the instance pool. If all the slots are filled, that machine can no longer run WebAssembly functions and may drop requests. Using Intel's memory protection keys, we can raise the limit on the number of instances available per machine. The technique, dubbed color guard in a 2022 paper, involves coloring different memory slots in the pool with different memory protection keys. Intel MPK allows us to fit up to 15 times more instances using the same amount of virtual memory space. Now, let us demonstrate how Intel MPK can be used in practice. We will use a benchmark infrastructure that spawns a WASMtime process, which is our WebAssembly runtime, to serve HTTP requests using an example WebAssembly module. This module does two things. One, it hashes the contents of the HTTP request body, and two, it sleeps for a number of milliseconds based on a custom header. This custom delay header is how we will mimic the effect of a slow server this function depends on. The longer we delay for this fake server, the longer the WebAssembly function takes up a slot in the pool. By hammering WASMtime with many concurrent requests, we can test the limits of the machine. We will now see this in a demo. What you see here is actual requests per second measurements of a process sending 4 concurrent requests to WASMtime, which runs a WebAssembly function for each HTTP request. We will now turn on the pooling allocator with 1,000 slots. Notice that the requests per second are now higher. The pooling allocator is generally more efficient at serving HTTP requests. We will now turn up the handling delay to 1 millisecond. Note how the requests per second go down when each WebAssembly function now has to wait for our mimicked delay server. We've used a significant delay here to make a point in this demo, but the idea applies regardless of this value. Now, each of the WebAssembly functions take up an instance slot for at least 1 millisecond. We will turn up concurrent requests to 500. Note how now the runtime cannot properly handle that number of requests. It doesn't have enough slots. Many requests succeed, but many fail. To further this point, we turn up the number of requests to 1,000. The failure rate is now even worse. We can improve the situation by adding more slots. And we turn the number of slots to 10,000. The situation is improved. However, we can only apply this technique up to a point. Eventually, we will run out of virtual memory space. If we want to run more instances, we need more virtual memory. And note, not more RAM, but more virtual memory space. We turn up concurrent requests to 5,000. Again, the failure rate increases. And when we try to increase the number of slots to 15,000, notice this time we have hit our virtual memory limits, and in fact, the controller has failed. To be able to increase the number of slots for WASM instances, we turn to Intel MPK. We will now turn on MPK. The kernel architecture has virtual memory limits, but Intel MPK allows us to sidestep them. With more efficient packing of the instance slot, WASM time can instantiate many more WebAssembly instances. Now Intel MPK is giving us much higher concurrent throughput per machine. We've demonstrated how Intel MPK can improve the efficiency of WebAssembly runtimes even when faced with delayed responses from external servers. The WASM Time project has a tool showing that we can use this feature up to its theoretical limit, 15 times more instances per machine. We expect other factors like I/O to become the bottleneck before that limit is reached. This feature and others is part of Intel's effort to make function-as-a-service workloads run great on Intel platforms. That concludes our demo. Here you can find a list of references to the workload and associated projects. Thank you for your time.